Okay, magnetic properties. Finally, the stuff that is directly pertinent to what all of you will be doing, because some of you will be dealing with quantum control of spin properties, others will have laser spectroscopy problems which are mathematically isomorphic to spin dynamics, and yet others will be using magnetic resonance as starting point for the data processing work that they will be doing. The first thing we must cover is, of course, how magnetic field enters quantum mechanics to begin with, and we start with Maxwell's equations, where, if you remember your physics, the electric field and the magnetic field component of the total electromagnetic field can be expressed via scalar and vector potentials. So the scalar potential is Z, the gradient of which is the electric field. Then vector potential, the rotor of it, is the magnetic field. And then we have this little time-dependent bit for the electric field that depends on the vector potential. All of this goes into our Hamiltonian. I will skip quite a lot of quantization and Lorentz invariance mathematics here and simply give you the final result at this level, that what we have is the usual kinetic energy and the potential energy, and if we have a moving charge, then the kinetic energy term is modified because a moving charge is a current. The current interacts with the vector potential, and then of course the charge itself interacts with the scalar potential, and all of this is designed, and if you work through the mathematics you will see it, that this is invariant under the sort of frame transformations that we have in special relativity. If you are sitting still and the charge is moving, then it creates an electrical current. If you are moving with the charge, then there is no current, but there is charge. But of course, energy must be invariant in appropriate ways with all the reference frames, and this is the quantity that is invariant. Now, if we put magnetic properties in, what we principally have is the uniform external magnetic field, and that is just the vector cross product B cross R, and the dipoles which have the cross between the magnetic dipole moment and the coordinate operator, but also 1 over r cubed in the denominator here. Now, if we take the curl of this and this, you can see clearly just immediately that the curl of that is going to be the magnetic field, and the curl of that will be the usual magnetic dipole interaction. Now, what is important here is that because this is a derivative, we have terms in these vector potentials that are inconsequential because they vanish on differentiation. For example, if we subtract some constant vector from here, then this curl isn't going to change. And so this is called gauge origin. And this is one of those quantities in physics which correspond to various fundamental symmetries of physical reality. For example, coordinate translation invariance, time translation invariance. And this is another kind of invariance which does not influence the actual physical observables, but all physical theories must have this as a symmetry in order to be correct. And notice also that this particular quantity diverges at infinity. If we go very far out in R, even though the magnetic field there might be very small, the magnetic vector potential would actually go to infinity. So you are starting to see all the inconveniences that people have in quantum field theories, where all of these divergences really come to the forefront and cause significant trouble. Okay, another quantity that adds to our problems is this arbitrary term in the vector potential, slightly more general than just the coordinate offset. You may remember from your calculus course that the curl of any gradient is 0, And so our magnetic field then, because it's the curl of the vector potential, has this extra liberty inside. If we add a gradient of any function to the vector potential, then the magnetic field is not going to change. So it's called a gauge function, and again this is something that is arbitrary in the definition of the vector potential. Likewise, the quantity here and the quantity here are invariant at the level of the magnetic field that they cause under the change of origin. You can see it immediately here. If we subtract yet another r from here, then nothing's going to change when you differentiate it. And a significant exercise in vector calculus would demonstrate the same invariance here. And these would be more or less avoidable complications in analytical calculations, but of course our calculations in electronic structure theory are numerical. We have chosen a basis. That basis would in many cases be atom-centered, like those Gaussian basis sets that we have discussed, and therefore the quality of description would not be uniform. Somewhere inside the molecule you do have plenty of Gaussians around you, and you can reproduce functions that you want, but if you are far away from the molecule in an atom-centered basis set, you wouldn't actually have any basis density around it, so the quality of the description would be awful. And then if we start looking at matrix elements of, for example, this commutator, right? If we want this d by dx operator, that is momentum, commutator with x, and we want the matrix element nm with it, well, we will have phi n and we will have phi m on either side of it, but let's just insert the identity operator, right? So the sum over k of phi k, it's that resolution of identity which we've already discussed in an infinite complete basis set. This would be the identity matrix that wouldn't cause any problems, but if we are far away from the molecule, then that and that would be terribly described, because there simply wouldn't be any basis functions in there. And so you can see the quality of description starts to depend on location, on how good the resolution of identity is in our location, therefore on the local quality of the basis set. And so all of these gauge troubles come to the forefront because it starts to matter where we have put the gauge origin in our calculation numerically, simply because our basis set is good enough for chemistry but certainly not complete. Okay, now with all of that in mind, we proceed to our kinetic energy term. So remember the minus q in there, the electron charge is negative, so we've made this a plus. E is the elementary charge, it is positive. We have the mass of the electron here, and we just open this bracket, bearing in mind that P is a differential operator, and so it might not commute with some function of the coordinate, and so we must be careful about how we open this bracket. So we've got P squared, we've got P dot A and A dot P, and we have the A squared there, and let's take a look closely at what these terms mean. This, of course, is our standard kinetic energy, momentum squared over 2m, but these will involve magnetic interactions. Okay, if we look at something simple, let's take something very elementary, like just the uniform magnetic field. So we put the vector potential of the uniform magnetic field, so B cross R over 2, so this becomes 4, this is B cross R this side and that side, and then we just work through the mathematics in here. We get this R cross P. R cross P, of course, is the momentum operator, and P is a constant, and so we have a coupling between the magnetic moment associated with the orbital angular momentum of the electron. Remember, the moving charge is a current, current is a magnetic moment will interact with the magnetic field, and so this is called the orbital Zeeman interaction for that reason, after Peter Zeeman. Then, if we look at A dot A in the uniform magnetic field, then we got B cross R, a little bit of vector calculus in here exposes this, And of course, the things that depend on the magnetic field quadratically are things like magnetic susceptibility. Right? In this case, this is called Langevin susceptibility. And I will not bore you with this mathematics. You can see it in the chapter 3 of the book, that if we start not with the Schrödinger equation and its energies, but with Dirac's equation and its energies, then after we eliminate the negative energies that are associated with antimatter excitations that we really don't need most of the time in our electronic structure theory, after we eliminate those terms, we start getting other kinds of effective terms. And in this case, that's the spin-orbit coupling. We will realize that we will get something where the spin is dotted with the orbital angular momentum, and a few more terms, mass energy and others, that I will not mention here because we really don't have the time for relativistic quantum mechanics in this course. And these two gentlemen are collectively responsible for a lot of that stuff. Right, so back to gauge invariance. We have our vector potential here in some gauge number 1, and if we add a gradient of some function to it, that will be a different choice of gauge, and we will call it gauge number 2. Then I will skip the corresponding derivation, but what will happen to the wave functions if we plug them into the corresponding Schrödinger's equation is they will encounter, they will just undergo a phase transformation. And as you know, and as is in fact expected from the definition of the gauge, the physical observables will be unaffected because this is just a phase term. And remember what we had in our observable calculations, that is the straight wave function, that is the conjugate, complex conjugate wave function. This times its complex conjugate is simply going to cancel, and so we are not going to have any difference. So the observable in gauge 2 will be exactly the same as observable in gauge 1. This should be G1, by the way, it's a typo. And likewise, the probability density will be the same in G1 as it is in G2. And in the simplest case, if our additional function is just the move of the gauge origin of the uniform magnetic field, we will have this extra phase term. And what this means is that we can account for this term at the level of our basis set. And these are called London orbitals, or in other term, gauge including atomic orbitals, which do have this term and therefore a measure of gauge invariance and therefore improved numerical accuracy when the basis set is not complete. And so when you specify GIAO in your magnetic properties calculation in a package like Gaussian, this is what it internally does. It adds those gauge multipliers to the atomic orbitals that you have. Okay, there were historically what could be called 3 classes of ways of accounting for the gauge origin. You could simply choose a single origin for the entire molecule, and that is not terribly accurate unless you are in the limit of a complete basis set, or you have a basis set that simply doesn't have a local quality problem like a plane wave basis set, for example. You could use various transformations that are somewhat better because they do account for the gauge origin at the level of each atomic and molecular orbitals, but really these methods are mostly of historical significance and I will not discuss them here. Or, as I've just shown you in the previous slide, you could associate a gauge origin term with each atomic or molecular orbital, and this class 3 methods is what is currently being used, and they are efficient in terms of the convergence of properties like, for example, chemical shift as a function of the basis set. Typically, if the basis is good enough for calculating high quality energies, it would also be good enough for calculating high quality magnetic parameters. And so these days, gauge including atomic orbitals more or less dominate, and all of this is just history. And that's an example. So you've got some Hartree Fox here and some DFT, exchange correlation functional here. That's the slope in the intercept for the calculation of, I don't even remember what this is. I think it's chemical shielding of some kind. You can see both SGO and CSGT actually can be pretty awful on the slope and the intercept, and the correlation isn't terribly good. And so we do need to move to London orbitals to get anywhere systematically in such small basis sets. But before we do that, we need to cover a little bit of extra mathematics, because as you will see in a moment, all of the properties we are going to be calculating, shieldings, J-couplings, hyperfine couplings, G-tensors, and so on, are derivatives of energy with respect to some parameters, and so we need to discuss ways of calculating those derivatives. So what is energy? Right? That's just the expectation value of the Hamiltonian for some wave function. Ground state, excited state, doesn't matter. So if we are differentiating the energy with respect to some parameter, we are differentiating this expectation value. And of course, both the Hamiltonian and the wave function can depend on that parameter. So we have a product of three things here that depend on the parameter. Thankfully, the product rule of differentiation does work in non-commutative cases. So we have a derivative of this times the rest of it, plus this term, then the derivative of the middle term, plus the third term, and then plus these two and the derivative of the last term. So this is literally just the threefold extension of the usual product rule of differentiation. Okay, let us take that and put it out in front. Let us actually act with this Hamiltonian on the wave function. So we will get the energy times the wave function. So the energy comes out in front and the Hamiltonian disappears. So we have the derivative times the function. And then likewise here, if we act with this Hamiltonian on the left, we will get the energy, we will get the wave function, and the Hamiltonian will disappear because that's an eigenfunction. So, okay, we have this and we have that. So much like we had the product rule here, we can use the product rule there, because look, the derivative times the function and then the function times the derivative. So that is the derivative of the product, psi. But of course, that's just the normalization condition, and these wave functions are normalized. So this is equal to 1, and 1 doesn't depend on alpha, so this is actually 0. And so what survives is what's called the Hellman-Feynman theorem, meaning that the derivative of the energy with respect to a parameter is the expectation value of the Hamiltonian derivative with respect to that parameter. And of course, Hamiltonian derivatives are really easy to calculate. If you have a derivative, for example, with respect to the position of the nucleus, well, you know where it occurs in the Coulomb interaction, right? Why don't you just differentiate that 1 over r? And that's easy. And then calculate the expectation value of the resulting operator with the ground state. And that is your energy derivative with respect to the atom displacement. That gradient of the energy that, remember, we were using for molecular geometry optimizations in the previous lectures. We will also need second derivatives, and for those, see the derivation in Feynman's paper or in my book. I will skip the derivation, but the second derivative is the expectation value of the second derivative of the Hamiltonian plus, and that is a very unfortunate plus, you have a sum over all other states in the system of this product of the first derivative with respect to parameter alpha and parameter beta, plus the complex conjugate of this quantity divided by the energy difference. Now, you may have seen similar expressions in Rayleigh-Schrödinger perturbation theory if you did a degree in physics. This is not perturbation theory. It looks similar, but it isn't. This expression is exact. And if you sum it over all the excited states, you will get this derivative to machine precision. So although they look similar to perturbation theory, this really isn't. Okay, so now let us put all of this to good use. We have discussed how magnetic field enters quantum mechanics. We have discussed all the gauge origin problems in incomplete basis sets and roughly how people get around them. This is a user level course, I'm not going into particulars. And we have looked at how to calculate the derivatives when we want them. Okay, the first and the most obvious magnetic property is of course the susceptibility. If you put a slab of material or some molecule into a magnetic field, it will get partially magnetized. And in sufficiently weak fields, for which basically read any reasonable field we can create here on Earth, even the strongest magnets, our induced magnetic moment is proportional to the applied magnetic field, and the proportionality coefficient is not a scalar, it's a matrix, and this is because certain materials are anisotropic and your induced magnetization needn't be collinear with the applied magnetic field, it can be at some angle, and so the proportionality coefficient here is a matrix. And then, of course, this induced magnetic field starts interacting with the magnetic field in its own right. And we do know the energy of this, that's minus mu dot b. But we also know the expression for mu from here. And so if we plug that here, we are going to have the energy equals b dot chi dot b. And therefore, if we are looking for this susceptibility matrix, the other name for it is the susceptibility tensor, because, well, a matrix is a special case of a tensor, that's going to be the second derivative of this energy with respect to the two magnetic fields. And to make it a matrix, we differentiate once with respect to B transpose and once with respect to B, and you should view it really as just a 3 by 3 matrix of second derivatives of the energy with respect to every component of the either field here. So d2e by dbx dby is, for example, the element 1, 2 of that matrix. Okay, and that's the derivative. And we've seen in the previous slide how to calculate it. So if we take our Hamiltonian and we compute the second derivative of the Hamiltonian with respect to the applied magnetic field, the term that is going to survive is this. So we will have that coming from the a dot a in the Hamiltonian a few slides ago. So that term here, just a bunch of coordinates. And this is again that same old familiar Langevin susceptibility. And it is a function only of the ground state of the molecule. Now, if we go and calculate the first derivatives of our Hamiltonian with respect to the magnetic field, we will see terms here like this, and that of course is the orbital Zeeman interaction, which I have discussed a few slides ago. You can see the orbital angular momentum interacting with the applied magnetic field, and it appears here, and this sum over all excited states is called one flex susceptibility, and that is the computationally expensive thing that is in particular responsible or perhaps caused by, whichever way you look at it, these ring currents in aromatic systems. Of course, they are conductive, and so they would have these ring currents if you put them into a magnetic field. And of course, there's a sum over all electrons in this case, and a sum over all excitations. And the nuclear part of magnetic susceptibility is usually exceedingly weak, compared at least to the electron stuff. And so in these calculations, it is commonly ignored. So when we're talking about electronic structure susceptibility, that's just the electrons that are responsible for it. Okay, so, and that's the general idea. You take the magnetic property, you express it as a derivative of the energy with respect to something. You use Hellman-Feynman theorem to calculate those derivatives, and then all of the Hamiltonian parts go in, evaluate all of these integrals, that is your quantity. Thankfully, all of this is automated and programmed and tested and released, and so as chemists, you are just the end users of this formalism, but you need to understand them, because next time you have a molecule with low-lying excited states, you might suspect that this determinant is going to become very small, therefore this quantity very large, and you might reasonably expect that molecule to be dominated by van Vleck susceptibility. Or if you have something where the first excitation is somewhere in the ultraviolet, like carbon dioxide, well, you can probably safely claim that its susceptibility is going to be mostly Langevin. Right? So basic reasoning and philosophy about these terms will inform your decision making, even if you are not looking into the technicalities of how all of these integrals are actually calculated and, well, even derived. Predictably, for what we've just seen, it wasn't terribly complicated. Magnetic susceptibility is calculated rather easily by even the basic things like the DFT methods. That's from the literature. You can see observed susceptibility against the calculated, nice diagonal straight line. You have to, of course, be careful if you do throw a genuinely multi-configurational electronic structure theory at it, it is going to fail. So that's an example of benzene molecule which is perfectly regular and well behaved, and you can see even Hartree-Fock does a very reasonable job compared to the coupled cluster SDT. But ozone, which really does have an eccentric electronic configuration, is all over the place, right? So CCSDT probably gets it right, but Hartree-Fock and DFT and even NP2 are off. But of course, most molecules you will realistically be dealing with, like amino acids, are in this class, and so magnetic susceptibility is easily computed for them. That's an example for you to meditate on. These tables are initially quite obscure, but then you look, okay, that's experimental value for the isotropic magnetic susceptibility, and you can see the quantities are not too different. The bigger and the more conjugated the molecule is, the more polarizable and magnetizable it becomes. But that's your Hartree-Fock continuous set of gauge transformations and London orbitals. You can see CSGT does fail. Right, it's pretty far from the experiment, but GIAOs, even for Hartree-Fock, are actually pretty close. This column is not too far from that column, and if you add the extra polarization functions, it improves. You go to B3-lip in DFT or other hybrid functionals. That's actually pretty close to here, and magnetic susceptibility is an easy property, unless you've got some eccentric electronic configuration like the one we've got in ozone. Okay, next item on the agenda, and this is already very close home. This is chemical shielding. This is what Anu here is computing as we speak for the paper that we are soon going to submit. And firstly, chemical shielding and chemical shift are different things. Chemical shift is something chemists had invented. They put a little bit of the reference substance, like tetramethylsilane, into their sample, and they calculate the difference of the frequency of the signal of interest and the frequency of that reference, and divided by the magnet frequency, and this is what they call chemical shift. Chemical shielding is a measure of magnetic screening relative to the bare nucleus in vacuum. All right, if we simply had just the nucleus, we would have E mu dot B, right, with the unit matrix in between. But the electrons turned up and screened the nucleus somewhat, and so this sigma is a measure of screening. And we can convert this chemical shielding to shift by calculating the chemical shielding in our molecule, chemical shielding in TMS, and subtracting the two. So essentially mimicking what chemists are doing. But all electronic structure theory packages will always give you chemical shielding, which is referenced to bare nucleus in vacuum. Okay, but let's take a look at what it is. This is E. That's the nuclear magnetic moment, that's the external magnetic field. To expose this bracket, we need to differentiate E with respect to mu, at which point mu is going to vanish, and then with respect to B, at which point B is going to vanish, and we will be left with 1 minus sigma, and with this extra minus in front, so sigma minus 1 is then D2E by d mu, db. Mu has 3 elements, b has 3 elements, so that's a 3 by 3 matrix. We must differentiate energy with respect to the nuclear magnetic moment and the applied magnetic field. Same old Hellman-Feynman theorem. We take the Hamiltonian and we know exactly from the previous slides how it depends on the nuclear magnetic moment and the magnetic field. So that's the second derivative. Then we need a first derivative here with just the magnetic moment and the first derivative here with just the magnetic field. We write down the giant Hamiltonian that I have discussed. We take those derivatives and here they are. The familiar old orbital Zeeman interaction turns up in dH by dB. dH by d mu, if you look at it, that's what's left of that vector potential of a magnetic dipole that went into the QA part of the spin of the Hamiltonian of the molecule, and you can see the orbital angular momentum like expression, except the orbital angular momentum refers to the electron and the distance is to the nucleus, and so this is called nuclear spin orbit coupling, right? So electron and the nucleus. And then we have nuclear shielding, similar, as you can see, to Langevin term, but we've got 1 over r cube in the denominator and just the coordinates here. So we plug that, and that in, take all of those integrals, and that is our chemical shielding tensor. Accuracy of that is, well, a serious function of the method. And the trouble, unfortunately, is that in a lot of cases you would have dramatic cancellation of errors in the basic methods that you have. If you look at the experimental data here, we have like 100 ppm, minus 30 ppm, and so on. You can see ostensibly, right, even Hartree-Fock not too bad. Well, too bad, I mean, depending, right? So here it's off by a ppm, but here it's off by 20 ppm, so significant difference. DFT is usually better, but in a lot of cases that's an error compensation situation. If you look at fluorine, for example, Hartree-Fock performs just as well or better than CCSDT, which is nonsense, of course. And the principal reason for that is that a lot of contributions to chemical shielding come from vibrational and conformational mobility of the molecule. And so for some random reason, for fluorine, for example, the error that Hartree-Fock makes has the opposite sign from the error that would result from vibrational averaging, and so the method looks as if it is performing well, but, well, it really isn't in practice. So health warning here, be very careful about which methods you choose for chemical shielding calculations, because you choose something that's too good, you will kill one side of the error compensation situation and the numbers might actually get worse. That's an example of that. I think that's a fairly regular case, which is quite rigid. That's the experimental carbon-13 NMR spectrum, just the line positions, no multiplicity, of course. Hartree-Fock gets it dead wrong. Möller-Plesset somewhat better. London orbitals on top of CCSD, somewhat better still, and then CCSDT gets it perfectly well. But the horrible thing about it, you add the extra level of accuracy on top of this, for example, solvent effects, because that's a cation, or vibrational averaging, and the answer starts getting worse. Right, so error compensation situations, and another table for you to meditate on, that is the various shieldings as a function of the basis set size in here across a database of molecules. So In systems with significantly anharmonic vibrations, conformational mobility, and so on, that vibrational and conformational averaging may be necessary. A notorious example is the difficulties with predicting chemical shifts of peptide bond nitrogens in proteins, because out of plane vibration of the nitrogen in the peptide bond is strongly anharmonic, but the chemical shielding tensor depends strongly on that out of plane displacement, and so in a lot of cases those nitrogen shieldings are inaccurate if you just do it for a fixed molecular geometry, and then the molecules are plainly just far too big for any realistic averaging with respect to the vibrational degrees of freedom to be done, because there's just too many of them, right? So at some point you run out of the supercomputer. More discussion of the accuracy here. You can see that is for carbon-13 chemical shielding. The Hartree fog is all over the place, right? That's the error, theory minus experiment averaged over some database. Möller-Placid, that includes a measure of electron correlation into it, is considerably better in terms of scatter, and CCSDT is of course really good for small rigid molecules where vibrational averaging is not a problem. Then you go, I think for something bigger in this case, oh no, that's the same stuff, but DFT. So 3 different exchange correlation functionals and 2 different ways of accounting for the gauge dependence in your orbitals, comparable as you can see, and significantly worse than MP2 and CCSDT for these molecules. Of course, you need to take solvent into account, and so this table is the effect of the solvent on the gas to liquid shifts for the shielding of water at different levels of theory. Again, something to take a careful look at and philosophize about when you have the time. We don't have, of course, the time to do that. The lecture is far too short. Next property, hyperfine coupling. If you are building a quantum device based on spin, this is both your blessing and your curse. Your blessing because, well, it gives you degrees of freedom. Your electron is coupled to your nucleus. Somehow you can push various coherences around. And the curse because, of course, decoherence is usually dominated by hyperfine mechanism. Some phonons are kicking around your crystal lattice, shaking your atoms. The moment the atom moves, dipole-dipole coupling to the nearby electron changes, and so you are going to have decoherence of your electron spin as a result of all of that stochasticity that takes place in the atom positions, even at very low temperatures. So this hyperfine coupling is a magnetic interaction between the electron and the nucleus. It has 2 principal contributions, which are really 2 mathematical parts of the same interaction. It's the electron-nuclear dipole-dipole interaction, but it has a singular part which can be visualized as just electron being either very close or in fact inside the nucleus. If you look at the nuclear structure, at a very high level, nuclei are in fact mostly empty inside, and so electron can fly straight through. That is called a Fermi contact interaction, and that's just a measure of the spin density of your electrons, so density of beta minus the density of alpha, and then just the isotropic interaction between the nuclear magnetic moment and the electron magnetic moment. In this case, basically just spin. And then we would have the magnetic dipole interaction at a distance between just 2 magnetic dipoles of the electron and the nucleus. That is the mathematical form of the magnetic dipole-dipole coupling. That is the integral over the electron probability density, because of course the electron is distributed over all the various fundamental constants in there, and that's the difference between the alpha and the beta density, which we have already discussed. This is the spin density of the unpaired electron. And there are further terms in hyperfine interactions coming from spin-orbit couplings and excited states. I will not discuss them because, well, we basically don't have the time here. This is how a geometric interpretation of a hyperfine tensor looks. You can show it as an ellipsoid, and the distance from the nucleus is the energy of the interaction, and then the angle is the orientation of the electron spin relative to the nuclear spin. There are many ways of visualizing them, and spinach, if you look at it, has a few ways of plotting these hyperfine tensors on top of your molecular coordinates. In this case, this is fluorine in a tyrosine cation radical, and of course fluorine has a lot of spin density, and so you have this giant hyperfine tensor in there. So particulars are again in chapter 3 of the book. Now, the important thing about hyperfine coupling is that contact term, which depends on literally the probability density of the electron at the nuclear location. And here we have a problem because, of course, we are dealing with nuclei as point charges, and if you are treating it as such, then your wave function at the nucleus point would have a derivative discontinuity. It's called the cusp. In other words, roughly speaking, there's a sharp corner in the wave function at the nucleus. But of course, Gaussian basis sets and plane wave basis sets are smooth. It is difficult to reproduce that corner. And for that reason, specialized basis sets have been designed by the group of Vincenzo Barone. They're very successful, donkeys years ago, but even now they're super useful. These are substantially just those double zeta and triple zeta basis sets, CCPVDZ and CCPVTZ, but they have been decontracted, so additional flexibility in the zeta count, and Vincenzo and company have added very tight Gaussians in the nuclear region and optimized the contractions to work specifically with the B3-Lip exchange correlation function. And so if you look here, these are the conventional basis sets, and the larger the isotropic hyperfine coupling, the larger the nuclear spin density, the electron spin density at the nucleus, the worse it gets. And if you look at Vincenzo's basis set, I think that's still the large polarized basis sets. I think I have the EPR2s and EPR3s, in the next slide. So this consistently underestimates the isotropic hyperfine coupling because of that smooth top effect. But if you look at the EPR3 basis set, firstly, you will see very sharp Gaussians in the S part of the basis, and secondly, you will see that these B3-Lip EPR2 and B3-Lip EPR3 combinations perform really well. One health warning here is that both have been designed to work specifically with B3-Lip. They might lose accuracy if you use a different exchange correlation functional, but well, this is what is currently recommended for the calculation of isotropic hyperfine couplings. So if you look here, B3-Lip EPR3 has got something that's pretty close to the experiment. It is more of an overestimate than an underestimate in this case, and it's generally the case for all the other parameters here. And that's all I had to say for today, and we will deal with J-couplings, G-tensors, and the rest of them in the next lecture. Any questions?